knows R is 0.08206 liters times atmosphere per mole Kelvin. You can measure, if you measure the pressure, temperature, volume, number of moles for a number of gases, and then get the ratio, it always comes out to R, the same value. R is equal to PV over NT. Okay, so this number comes from the data here. But your book also uses other units of R. And so we don't have to use these units, other units. So for example, if we don't want atmospheres, instead we want torr, then we do something like this. Maybe 0.08206 liters atmosphere per mole Kelvin. And then we need to convert atmospheres into torr. Do you know how to convert atmospheres into torr? Yeah, it's 760 torr per atmosphere. And so then the atmospheres cancel, and that gives us liters torr per mole Kelvin. What does that come out to? So if I do this, we get 0.08206 times 760. And this comes out to 62.365. And the units here would be liters torr per mole Kelvin. And so this equals 62.365 liters torr per mole Kelvin. And so torr is a common unit, or millimeters of mercury. Millimeters of mercury is the same as torr, so it would be the same. But you know, it's torr, and did you know torr and atmospheres are not the SI units for pressure? Do you know what the SI units are, the international system? Hmm? Yeah, pascals or bars. Bars. Pascals or bars are the more common. A pascal and a bar, numerically the same, just different decimal place, like, you know, kilograms and grams. And so let's say I don't want torr, I don't want atmospheres, I want bars. So this is 0.08206 liters times atmospheres per mole Kelvin. And then do you know the conversion for atmospheres to bars? You don't have to have it memorized, but there's 1.01325 bar per atmosphere. So what does that come out to? 0.08206 times 1.01325 comes out to 0.0831. 0.083114 liters bar per mole Kelvin. And so the equivalent to this would be 0.083114 liters bar per mole Kelvin. Do you want to memorize these three? No. Neither would I. What I recommend is this. Just memorize one. Why bother memorizing more than one? Which one do you want to memorize? I recommend memorizing this first one. Don't bother memorizing these two. Why? Because if you're given torr, then it's much easier just to convert it from torr to atmospheres. If you're given bars, it's just much easier to convert that from bars to atmospheres. So we'll just do the conversions for the individual units. Your book doesn't do it that way, though. Your book uses a different constant, R, depending on what's given. And so take a look at this. nRT, N, 0.0888 moles, R, 62.4 liters torr per mole. Where did they get that? They memorized it. And so your book has a different approach. Your book is just going to say memorize these three. Do you want to memorize those three? No. Or get them. Whereas me, it's much easier to do this problem this way. This problem, okay, we're given moles. So N is equal to 0.0888 moles. V is 5.00 liters. T is 36 degrees C. 36 degrees C plus 273. Plus 273 gives us 309 Kelvin. Okay, and then we're solving for P. Well, you know, the easiest thing is just to solve for P, the standard units. What are the standard units of P? Atmosphere. So P is equal to nRT over V. And so I would have done this problem differently. So N, 0.00888 moles, R, 0.08206 meters atmosphere per mole Kelvin, T, 309 Kelvin. So Kelvin cancel, moles cancel, and then PV is 5.00 liters, so liters cancel. This is going to give me the answer in atmospheres. So, see what it comes out to. 0.0888 times 0.08206 times 309 divided by 5. .4503 atmospheres. And then we can convert that to torr, 760 torr per atmosphere. .342 torr. And so this 62.4, I wouldn't memorize it. However, your book loves torr, and so maybe in that sense it's useful. And most people use millimeters of Hg, so it could be pretty useful. All right, let's take a look at number 4. 0.917 mole sample of hydrogen gas at temperature 25 degrees C is found to occupy a volume of 27.1.7. What is the pressure? So we're solving for pressure. We got moles, we got Celsius. So moles is good. Celsius, we got to convert to Kelvin, so that would be 290.2 Kelvin. And then volume in liters is fine. We're going to get the pressure in atmospheres. Once we get the pressure in atmospheres, then we'll convert it into torr. So this problem is just like the previous one. Number 5, the pressure exerted by 6.04 moles of nitrogen monoxide at a temperature of 18 degrees C is 17.2 atmospheres. So we have the number of moles N, we have the temperature T, 18, convert that to Kelvin, and then we have the pressure in ATM, so we're just solving for the volume. The volume is going to be in liters using our value. 8.39 liters is what they got. 6 is the same, calculate the volume in liters, except here, moles, that's fine. The pressure, they give us the pressure in torr, 872 torr, so I do one step, and that is convert torr into atmospheres. For the temperature, we got to convert to Kelvin and solve for the volume in liters. 7. A 784 milliliter hydrogen lecture bottle is left with the valve slightly open. Assuming no air is mixed with the hydrogen, how many moles of hydrogen are left in the bottle after the pressure has become equal to an atmospheric pressure of 752 torr and temperature of 22 degrees C? So what we're doing is we're solving for moles again. We have the volume, it's in milliliters, so we'll have to change volume from milliliters to liters. And then we have the pressure in torr, we'll have to change it from torr to atmospheres. And the temperature in Celsius, we're going to have to change it to Kelvin, and we're good. Again, they don't do it like I would have done it because they use this other one here. But we want to minimize the amount of memorization we have to do. The sample of xenon gas collected at a pressure of 1.18 atmospheres. So we don't have to do anything with that pressure, that's fine. Celsius 18, so we've got to change that to Kelvin. And volume of 26.7 liters. So how many moles? So this is the same thing, moles, sulfur N. At what temperature in degrees C will 0.810 moles of chlorine in a 15.7 liter vessel exert a pressure of 756 torr? So we're calculating the temperature, but the temperature is going to be in Kelvin. So we're going to have to do this before calculating it. We're going to have to change torr into atmospheres. We solve for the temperature in Kelvin, and then we'll have to do one additional step, and that is to convert Kelvin into Celsius. Again, your book's not going to convert torr into atmosphere because they're going to use this other version of R here. But we would convert torr into atmospheres and then use our standard version of R here. R is in the denominator. That gives us, this should be equals, not times. Equals 235 Kelvin. So to convert Celsius into Kelvin, we add 273. In order to reverse that, we have to subtract 273. So we're going to subtract 273. We're going to get minus 38 degrees C. 10, a 0.142 mole sample of argon gas, so we got N, has a volume of 834 milliliters. So we have V, but we need to convert that to liters. And we have P in atmospheres. What is the temperature of the argon gas in Celsius? So again, we're going to calculate the temperature in Kelvin and convert it to Celsius. Number 11, how many moles of carbon monoxide must be placed into a 40.0 liter tank to develop a pressure of 965 torr at 18 degrees C? The volume's okay. Pressure, I'll change it to atmospheres. Temperature, I'll change it to Kelvin, and then just solve for N for moles. N is equal to PV over RT, 2.13 moles. 12. The sample of neon gas is collected at a pressure of 0.946 atmospheres. So P I don't have to change to the atmosphere. T I don't have to change either. That's in Kelvin. V I do have to change. I have to change that from 712 milliliters to liters. 0.712 liters. How many moles of neon gas are in the sample? So you just use this equation, plug in everything. 13, find the volume of 0.621 moles of helium at minus 32 degrees C, 0.771. So we're solving for V in this case. So moles is okay, temperature we got to change to Kelvin, and pressure is okay in atmospheres. And so they should be using the other value of R here. It's not so difficult to memorize two values of R, you know, one liters torr per mole Kelvin, CZ2.4. However, I want you to memorize R, when we use liters atmosphere per mole Kelvin, I want you to memorize R to 4 sig figs. So the 3 sig figs is 0.0821, the 4 sig figs is 0.08. Yeah, 0.08206. So we do that, we calculate the volume here. A sample of neon gas collected at a pressure of 531 millimeters of mercury and a temperature of 291 Kelvin has a mass of 10.2 grams. What is the volume of the sample? And so here we have the pressure in millimeters of mercury. We need to convert that to atmospheres. The temperature we don't need, it's already converted to Kelvin. The amount of neon is in grams. We don't put grams in here, we put moles. So we're going to have to do a gram to mole conversion using the molar mass of neon. And we can get the moles. Okay, those are your basic, solve for a single variable. Now we have some specialty applications of the ideal gas. So let's talk about some of the applications. Other applications of the ideal gas law, PV equals nRT. One is this. It's the more comprehensive or complete combined gas law. So other applications would be the combined gas law. The combined gas law says this: PV equals PV over NT equals R, which is a constant. And so this ratio never changes. PV over NT, it's always equal to 0.08206 liters atmosphere per mole. Therefore, we can do this. P initial, V initial over N initial, T initial is equal to P final, V final over N final, T final. Does this equation look familiar? It should. This is a combined gas law. The only difference is now we have N if the number of moles change. And so what you could do with this is you could add additional gas. You add additional gas, it's going to change things, or you can remove gas. And so the number of moles initial doesn't necessarily have to equal the number of moles final. That is, if we have a container of gas, we can leak some gas out of the container. That is, we're losing moles of gas, or we can add some moles of gas into the container. That'll change the pressure of the container. And so this is a more comprehensive version of the combined gas law that we encountered earlier, in which the number of moles can change. So that is, we can add gas to a container or remove gas from a container. All right, that's the combined gas law. The next application we're going to look at looks like the density of a gas. The density of the gas is equal to the mass over volume. Mass over volume. But we know that a gas volume, the volume of gas is equal to nRT over P. And therefore, what we can do is we can substitute that in here for V. V is equal to nRT over P. And then invert and multiply. So we're going to get the mass times pressure divided by nRT. Well, when we look at this, mass over N, do you know what mass over N is? Mass is typically in units of grams, and N will be in units of moles. So grams per mole is called what? Grams per mole is called the molar mass. The molar mass is equal to the mass over N, gram to mole ratio. And so this is going to simplify into the molar mass times P divided by RT. So if we know what the molar mass of the gas is, we can calculate its density at any pressure and temperature. And so with this equation, we can calculate D, density, at any temperature and pressure. And so there's a special temperature and pressure called STP. For example, STP. STP is called standard temperature to 0 degrees C and pressure, which is 1 atmosphere. So standard temperature, 0 degrees C, standard pressure, 1 atmosphere. This is for the USA. For the rest of the world, it's like this. The standard temperature, STP, standard temperature is 0 degrees C, but standard pressure is different. You know what the standard pressure is? The rest of the world? Bar. 1 bar. So what are they doing? Are they doing bar or atmospheres? Bar? All right, we're going to do bar too. So we'll just pick this one. 1 bar. So we're going to use our density equation. Density is equal to molar mass times P divided by RT. Molar mass times P divided by RT. All right, so that brings us to a problem like number 16. What is the density of a sample of oxygen gas at a pressure of 1.40 atmospheres and a temperature of 49 degrees C? Is that under standard temperature and pressure? No. Yeah, mixed up. I shouldn't have done density first. I should have done the molar mass first, but it's all right. We'll look at number 16. Well, first off, what is the molar mass of oxygen gas? Each oxygen atom is 16, so there's 2 of them, so this is going to be 32.00 grams per mole. Molar mass. The pressure, 1.40 atmospheres, and the temperature is 49 degrees C, which in Kelvin would be 273, 310, 322, 322 Kelvin. And so we just plug everything in here. 32.00 grams per mole. Pressure, 1.40 atmospheres. R is our standard R, 0.08206 liters times atmosphere over mole is Kelvin. And T, 322 Kelvin. And so we got to make sure this equation is correct. The way you make sure that equation is correct is you make sure the units cancel each other out. Leave you with the correct units. So atmospheres cancel, Kelvins cancel, moles cancel, and that leaves us with grams per liter. So density in grams per liter, that sounds correct. What is it? It's going to be 32 times 1.4 divided by 0.08206 divided by 322. 1.695 grams per liter. So it's about 1,000 times less dense than water. You know, water is about 1 gram per liter. Almost 2,000 times less dense. 17. The effective molar mass of air is 29. So if I have a mole of air, so air is a mixture of oxygen and nitrogen. If I have a mole of air that's 6.022 times 10 to the 23rd air molecules, and those are going to weigh 29 grams, that mixture molecule. Use this value to calculate the density of air at STP. Why don't you try that? Calculate the value at STP and at 20 degrees C and 751 torr.